present for you the conformity assessment that you can do based on analytical results. And this is a Eurachem guidance on compliance assessment that is rather recently. So there is the guide, which you can see here, but there is also a leaflet that you can have, which introduces the guide. So it's like an aperitif to the guide, you could say. So when we are talking about compliance, we need to go back to the measurement cycle. We have a client that has an issue. This can be, for example, if the toy is safe, if the blood alcohol is over a limit, and we have to define this issue and do the eventual sampling analysis, and then we come up with a result. And we would say that we have measurement quality if we can decide that this toy is safe or this driver had too much alcohol, so he will be punished. So the decision or result is the critical issue. So this is the second edition of uncertainty information in compliance assessment. And the issue is whether a result complies with a specification, for example, the nickel concentration, a regulatory limit, for example, a toy, or legal limit, for example, blood alcohol. And we can have 5 different cases. If we start from the left, we can have a measured value, excuse me, clearly above the limit, but we can also then have a measured value which is close to the limit and on the limit and slightly less than the limit. And it's these cases marked 2, 3, and 4 where we have problems, where we need to have guidance to come further. And the really good thing we need is the decision rule. So we talk about conformity or compliance. Well, ISO uses this conformity assessment, and this can be for anything. But here we concentrate if a measured result complies with a limit, and then we use the word compliance. ISO 1725 says that if the result is compliant, we can make a statement on conformity. Anyhow, we talk about compliance. And just to give some examples, we can test a toy. It has, for example, to be a certain size of a toy if it should be used by children below 3 years of age. We can look at the industry. We can have a produced high alloy steel, and the mass fraction of nickel should be between 16 and 18%. We can also have a legal one. The driver has a measured alcohol level. Can this be confident that this alcohol content in the blood is actually over the limit? And we can have food, if there are any residues in the food that is above the maximum value. In the guide, we have cases that we do not cover, and this is manufacturing. Because if you work in a process and you have to decide from the quality control results obtained today that the production process is or is not under control. And in this case, we shall not look at the uncertainty. I think this is a very important issue, that if you are a production lab and to the process, you shall not communicate your uncertainty, but you should communicate the variation you have for the results over time in your laboratory. That is what we will call the within lab reproducibility. And that should be used to take decision if the process is or is out of control. Of course, you also need to take a second sample if you have problems with the process, but that's another issue. So let's look at some terminology. We talk about decision rules. That is the rule that describes how measurement uncertainty is accounted for when stating compliance. It can also help the user by specifying a lot of details. I will come back to that. Then we have a specification limit or a tolerance limit, which has maybe just an upper or both upper and lower bound for the permissible values. From the decision rule and specification limit, we construct acceptance limits. These can actually be the same as the specification limits. Then we talk about shared risk, but they can also be changed. So for example, if we want to focus on correct reaction, then the reaction zone decreases. And in the lower part here, we focus on correct acceptance. That means that we put a guard band to the left side of the upper limit. So the acceptance zone decreases. We can also have this, what we say, simple acceptance or shared risk. And that says, we just take the specification as it is. This has been used a lot. When we, for example, at RISE control the petrol pumps, we use this. We see that we have a good measurement of the volume of the petrol with a very low uncertainty, and we just use simple acceptance. In my opinion, if the rule is simple acceptance, we need to state a maximum uncertainty, because otherwise it can be too big risks for both the user or the producer. I will take some simple examples. We have steel, for example. The specification zone is from 16 to 18. We have a measured value with 16.1. With simple acceptance, of course, the risk is shared and the batch is compliant, but it could be different with another decision rule. So let's look at the information we need to make assessment of compliance. Of course, we need to have a measure and very clearly specified. This is the total concentration, for example, or dissolved or leachable. We have to have a measurement uncertainty, and that should be stated at the upper or lower permitted limit. So we want to look at the uncertainty at the limit, not at the result. This is extremely important for compliance. We need a decision rule, and we need a measured value. I will give you an example for a batch of steel, we just talked about. Here we know that the uncertainty is about 0.2% nickel, taking into account sampling and analysis. That means that the standard uncertainty is 0.1% nickel. Now we want to have high confidence of correct acceptance. We want to be very sure that the nickel value is between 16 and 18. That means that the acceptance zone will be decreased. Here we assume a normal distribution, and if you do that, you can calculate a guard band, which, if we look at just one side of the tail, if we have this 95%, it's not 2, it's 1.64. And if we do that, we get an acceptance zone from 16.2 to 17.8 instead. And the measured value is 16.1, and it's not compliant. Let's have a look at it, how it looks. So here we have the original specification, and here we want high confidence of correct acceptance. We want to be sure that the nickel, the really true value of nickel is between the specification. Then we put the guard bands, so to say, inside. So that means that for a lower limit, we put a guard band on the right side, and for the upper, and we actually decrease the acceptance zone. And in this case, the batch is actually non-compliant. So the decision rule is the key. And it should have a well-documented method of determining the acceptance and reaction zones, for example, with the guard band. But in many cases, we can have different decision rules. So we can have this pass-fail. We talked about simple acceptance. We can use guard band. We can also have decision rules stating that you can have pass-fail, or if you close the limit, inconclusive results. And this can, in many cases, be very good to have, but of course you maybe need to do something else. And that can also already be defined. sorry for that, defined in a two-stage procedure, that you do something screening and then you do a second analysis. I think if you are far away from a limit, there is no problem. There is not an issue. But we need to have better guidance if we're close to the limit. And the decision rule can actually give more detailed information to help you here. So, for example, as we talked about, if you have shared risk, you should specify the maximum uncertainty. We can also look at the distribution of the results. Normal, we would normally say if you have less than expanded uncertainty of 30-40, but if you are over that, you may regard it as a log normal distribution, especially, for example, in microbiology. We also need to have rules for rounding before assessing compliance. For example, if you have 16.17 and if you round that to 16.2, maybe you get a different result, or if you compare with the original 16.17. The number of replicates you need to do, and also if each replicate has to be compliant, or the mean value or the median value, and also if you find outliers, how to deal with that. All this, of course, helps when you have to make your decision. They can also be produced for further action. We already talked about non-binary decision rules, for example, with inconclusive. So it's pass, maybe, or fail. We can also, in the decision rule, recommend how to report and also how to state which decision rule we used. And according to ISO 1725, you need to state the decision rule when you make compliance. Now, if we come to higher uncertainty, we usually see that we have asymmetric distributions. And I told you that is already well known in microbiology. And then we can see that a good approximation is to see the distribution as log normal. I will give you a short introduction here. So if we would have assumed normal, and we would have an upper limit of 100, and we would have a relative standard uncertainty of 0.3, that's 30%. That is 60% expanded uncertainty. So this is relatively high. We would have the acceptance limits between 51 and 149. But if we would assume log normal, which would probably be a better assumption, the acceptance zone will be shifted up right. So the lower will be 61 and the higher will be 164. And let's look at this. We can use something we call the uncertainty factor to calculate these acceptance zone. So if you have a relative uncertainty, and we would also use a K factor of 2, you can take the exponent of K times URL. And if you do that, for an example here with 30%, we will get a factor of 1.64. Then we can multiply the uncertainty factor with the limit, and we get the value of 164, which we had shown here. That correct reaction, the acceptance limits goes up to 164. And the uncertainty factor for the lower limit is just by dividing. So this is an easy way to estimate the reduced acceptance zone when you want to have correct acceptance. So let's take an example here. We have the mass fraction of a banned substance. And the relative standard uncertainty in this case is 35%. The upper permitted limit is 2 nanograms per gram. And we will, in this case, have high confidence of correct reaction instead. That means that the reaction zone will decrease. In this case, we have such a high uncertainty, so the distribution is assumed to be log normal. We know that the K factor is 164, So we can calculate the uncertainty factor as 1.64 times the URL, which was 0.35, and we get a factor of 1.78. Then we can calculate the guard band that we should put to the right of the limit to have high confidence of correct reaction, and this would be 1.6 nanograms per gram. So we have an acceptance limit of 3.6 nanogram, and we have a measured value of 3.3 nanogram. That means that it will be accepted. But let's look at clearly at these distributions. So if we would have assumed a normal distribution, then the value would have been over the acceptance limit and would be rejected. But since we know that we probably would have a log normal distribution, is a better assumption, then the acceptance limit will be higher. It will be 3.6 instead of 3.3. And that means that the measured value is compliant. We talk about some other issues in this guide. We talk about prudent user and consumer risks. We have already said that we talked about inconclusive results. And we also talk about something which is very important for a manufacturer, specific or global risk. Because we could think of a specific risk, that is a risk for a sample, but we can also think of a global risk over time. What is the risk? There is a lot of documents on this, and they come from ILEC and from GCTM, for example. So let's summary. The key in decision is the decision rule, and together with the specification limit. And the decision rule can be hopefully very detailed in order to help you to make the decision. And from that, we can calculate the acceptance limit, which could be the same, that is shared risk, which was very common previously. And then you need to have a statement of max uncertainty. But it can also be using a guard band, where we can focus on correct reaction. Then we put a guard band on the right side of the upper limit, and the reaction zone will decrease. Or if we focus on correct acceptance, we put the guard band to the left of the upper limit, and the acceptance zone will decrease. So the different decision rules we already talked about: the simple acceptance, the guard band, the inconclusive, and the two-stage procedure are discussed. And these are also discussed in the ILAC and ECGM documents. So here are the guidance from Eurachem. Please read the leaflet first as an introduction before going into the guide. So I will thank you very much for listening. And there is more information about measurement quality and, for example, about compliance, but also on the analytical method at this site, www.trollboken.se. So thank you very much, and I will now be able to contact you for questions. So all the best, and thank you very much.